Yes. Let me just stop this. Okay. So next thing we're going to do is Faraday's law. Faraday's law, basically, we talk about a few things. Talk about Faraday's law, talk about a thing called motional EMF, and we talk about Lenz's law. And then we're going to talk about these Maxwell's equation business. So the first three are really test material type stuff, watch out for it. And then the last two, again, is building that foundation for future courses. So let's talk about Faraday's law. And I've got some videos online which kind of show this stuff occurring. But basically, I can describe it here. So we have a coil, and we have a magnet. And we simply connect the coil to a galvanometer so that it can show very sensitive current flowing. And what we see is if we push the magnet into the coil, we'll get a deflection of the needle showing that current is flowing. If we stop, the current flow stops. If we pull the magnet out, we get a deflection of the needle in the opposite direction. If I change the polarity of the magnet, I get the deflection in the opposite direction. So if it went to the right with the North Pole when it was approaching, it will go to the left with the North Pole, with the South Pole when it's approaching. So it knows which pole I'm moving and in which direction it matters. But the key thing is it's got to be moving. I can get the strongest magnet in the world and just park it in that coil, and the coil won't respond. It's not about magnetism. It's about the rate of change of the magnetic field. It's like the rate of change of magnetic flux. That's what counts. Not the amount of flux, but the way in which the flux changed, the rate at which the flux changed, which is, let's face it, is weird. It's like it's a strange kind of interaction. And okay, I like electricity, carries energy. I can use a mechanical system to create an energy carrying electrical system. So this is the basis for my generator. In the power station, we don't have a whole bunch of people with magnets moving them backwards and forwards, but we have a coil that spins inside a magnetic field. Move the coil instead of the magnet, same thing. So we spin the coil inside the magnetic field, and that gives us a constantly changing magnetic flux going through my coil. And that means that I continuously creating this current. The magnitude of the current will vary depending upon my geometry. So as time passes, I'll get positive and negative current flow. That's AC. But it just comes directly out of this. So this is the beginnings of electricity generation. So we say an EMF, electromotive force. Oh, I didn't go to my pen, sorry. You can say, let's get a pen on this. Okay. An EMF, that's an electromotive force, which is measured in voltage. An EMF can be induced in a coil by changing the magnetic field position. The magnetic field can be changed also in time instead of position. So I can move the magnet and leave the coil still. I could move the coil and leave the magnet still. If I could change the strength of the magnet and leave everything still. Doesn't matter. I just got to somehow change the flux lines going through that coil in time. However I do it. That's the neat thing. So here's another example where we have, this is just a DC voltage source, and we have a switch, and we have a electromagnet when current flows through it, and it's connected using a soft iron yoke to a receiving coil, which is connected to the galvanometer. So whereas on this side I move the magnetic flux in time by moving the magnet, I can move the magnetic flux in time by turning on or turning off this battery. I cause current to start flowing. It increases rapidly. That's like moving the magnet really close quickly. I turn the current off. The magnetic flux falls quickly. That's like moving the magnet away quickly. So by just clicking that switch open and closed, I will get a signal on that side. So, okay. When I look at this, I say, well, there's Faraday's law. Faraday's law, the EMF that is induced in a circuit is directly proportional to the time rate of change of magnetic flux through the circuit. Let's put that down in shorthand. The EMF is proportional to, well, it's going to be equal to a constant times this, the constant's 1, if I do my numbers right. D phi B by dt, the time rate of change of magnetic flux. Negative sign, just because I got to keep track of, is it adding to or taking away from? So I need some nomenclature there for signage. Just remember it's a negative sign. Supposing, rather than having one loop, I have 25 loops in a coil, then presumably the effect is 25 times greater. So, yeah, okay, we put our N inside there. That's the number of turns in our coil. So, decision, decision, decision. Do you learn that and have to remember about the N, or do you learn that and have to remember what N is? It's up to you, but, you know. If you miss the N, you lose points if there is a coil. So one way or the other, yes.
Two questions. One for N, is that the loops of the secondary coil?
So yes, this is it's the flux. It's the flux going through this coil, and it is the number of turns of this coil. And thanks for asking that question. Yes. That guy.
Yeah, that whole deal with that, be changing the magnetic field, like constantly back and forth,
Yes.
that would create a large EMF or whatever, or consistent EMF.
Not consistent EMF, but an EMF which would fluctuate on this side.
Okay.
And you just invented a transformer. And the transformer is the critical reason why DC failed and AC won. In the battle between Edison, who was DC, and Tesla, who was AC, DC failed. And the reason why DC failed, there's a number, but one of the reasons why DC failed is you can't really change it easily. Whereas with a transformer, I can switch off between high voltage, low current, or low voltage, high current easily using transformers. And it makes it very, very versatile. So it's a really important issue, yes.
Is that why most battery operating things are DC? Because DC works better on smaller circuits?
So, well, if I was to... So batteries by their very nature are DC because they're a chemical process. And I could put an inverter in there which would make them into AC, but inverters are very expensive.
Oh, so it's a cost thing, not an efficiency.
It's a cost thing. At least there is a cost element to it.
What about like cars?
But then the question is, do you... so then the question is, do you get an advantage by making a DC thing into an AC thing? Yeah. And often you don't. Frankly, if you look at the circuitry inside your television, then most of it's DC. What we find is AC is great for delivering power. Once you've delivered the power, when you want to do any kind of signal processing, DC's the way to go. Electric fire, my air conditioning system has been having problems. And so I went out and bought an electric fire for the house because it was like just unreliable. And it's AC, and I can't imagine making a DC electric fire, but in principle I don't see why not. You know, maybe the electrical engineer would say why not, but... Oh, a little. It's literally a resistor. It's a coil resistor, which glows. Oh, space heater. It's the language. It's the language thing. I thought you'd never seen an electric fire, but it's a language thing. And it's very good actually. With the modern technology has not improved the heating effect, but it's made the fictitious fire look really realistic. So whereas when I was a kid, we had a radiant heater, which what did you call it? Space heater. Yeah, we had a space heater that just was like an orange little filament, and we just looked at it. We all sat around looking at it, kind of like trying to get warm. And now we can sit around looking at this like flame that you can even click a little, you can change the color of the flame, which I just think is like, and for some reason I like the one with a little bit of blue in it. It's like, I just feel warmer when I see that thing, you know? So very important equation, Faraday's law. I'd like you to know Ampere's law and Faraday's law and Gauss's law, for instance, by their name. Because people talk about, oh, Faraday's law. And if you're going, well, which one is that? You'll come across as being a bit less experienced. So do take the trouble to learn them by their name. So Faraday's law, it doesn't matter if the end's in or not, but, you know, Faraday's law is Faraday's law. A coil of wire consists of 20 turns. So let's do this one together. So my coil of wire, I kind of draw my coils of wire a bit like that. I draw them like that. And I say N is equal to 20 turns. Magnetic flux through the coil of wire, so my phi B. So I'm going to go phi B. Changes, so phi B initial equals going to be 8 Tesla meter squared. And phi B final is equal to 12 Tesla meter squared. And then the time interval delta T is equal to 4 seconds. So I've extracted from my words that visualization. Now let's do some principles. So my principle is the EMF is equal to minus N d phi B by dt, which equals minus N. When things are going nice and uniformly, then we can just use the delta, which equals minus N. It's going to be phi B final minus phi B initial over delta T. So my EMF is equal to minus, and my N is 20, and my phi B is 12, minus my phi I is 8 over 4. So that's going to be minus 20 times 4, oh man, over 4. E is equal to minus 20, and the units are going to be volts. Did I do that right? I think I did that right. 12 and 8 makes 4. From a teaching point of view, I wish I'd used different numbers so I didn't get 4 over 4, but you know, hey, that's the way it goes. Okay. Let's play with it. The trick is changing my magnetic flux, the number of arrows going through my coil in time. And there are 3 ways that I can do that. I know that because I know that my magnetic flux is equal to B dot dA. We just did that. And I know if I expand these vectors, this vector dot product, I get B times A times the cosine of the angle. So there are 3 ways I can change this. I can change my B, leaving the A constant and the angle constant. I could change my A, leaving the B constant and the angle constant. I could change my angle, leaving the B constant and the A constant. Or I can do a bit of all 3, but we tend to do one or other of these. So what would this be? The B would be increasing the magnetic field strength somehow. And the A would be distorting my coil, making it bigger or smaller. They're both pretty hard, actually. It turns out the easiest thing to do is just spin the coil inside a magnetic field. So I don't know what you feel, but for me, I look at this and go, oh, I don't want to mess with that because that's trig, and I still have middle school nightmares about trig, you know. But it's actually, from a mechanical point of view, the way to go. That's what power stations do. They spin the coil. They don't try and change the area of the coil, and they certainly don't try and change the magnetic field strength. They just spin the coil. That's the way to go. But we want to know what happens if you were to change the area, or you were to change the magnetic field strength. So by simply substituting this into my top equation, I get the, if you like, the fuller version, which is E is equal to minus N. You've got to decide if you want to put N in there or not. D phi B by dt, which equals minus N d BA cosine theta by dt. And I don't learn this as a separate equation. I hope you won't too. I know this one and I know that one, so I know the answer. I can figure it out. Okay. I want to change this question because I messed up. And I gave you a second question, which is all about flux. And then I changed the area. So I want to do one where I changed my magnetic field strength. So I'm going to say a coil of wire consists of 40 turns. So let's draw that. And you know, I don't know what you feel about that, but for me, putting down that like coily shape just visually reminds me that I'm dealing with a coil rather than a loop, so I'm less likely to make that mistake. A lot of this is putting prompts down that nudge you away from walking off a cliff. So by drawing loops as a single thing, but coils as a bit more, if I get into that habit, I'm less likely to make that mistake. My friend's husband, she was telling me that he trained himself to always put the kettle back onto the ring on the stove, because a few times he'd walked out and he'd left the ring on and put the kettle down on another ring and he didn't catch it. So he reckoned the way to avoid that is I put the kettle down back on the ring, and frankly, if the ring's on, I'll see it, but also I'll hear the bubbling of the water again. So he trained himself to do that. And so part of it, I think, and this is where practice comes in, part of it is kind of recognizing what your typical mistakes are and then trying to train yourself so that you don't make that mistake. I've got an issue at the moment in that our new gas stove, when you put it on low, you can hardly see the flame. We have a gas stove. You can hardly see the flame, and I'll make an egg. I like it to be really low heat. I've got this tiny little frying pan that only does one egg, so I have this really low heat. And then I'll make my egg sandwich, which if you've never had an egg sandwich, it's like the best thing in the world. And then I will eat my egg sandwich, and 2 hours later I'll come back and the ring will still be on. Which is, frankly, my mum had a stroke, and one of the tests they gave my mum to see whether she could live by herself was did she leave the stove on? And she did, and so they said, you can't live at home by yourself. You really have to come from a safety point of view. We have to basically, it's time to institutionalize my mum, which in the family caused tremendous traumas. And my wife, who knows this story, was saying, maybe it's time, there's one down the road, we'll just send you along. So a bit traumatic for me. So you had a question or comment?
I was going to say, do you still use a conventional kettle or do you use an electric kettle?
I use an electric kettle. It's like, although they'd leak. It's like I'm on my 5th electric kettle. I finally bought one that's made out of metal rather than plastic, because the plastic ones just kept leaking. You're thinking, we've had kettles for 100 years. You think we could have sorted that problem out by now. Anyway, so I'm going to change this question. So the number of turns is 40. The magnetic flux through the coil, magnetic field. The magnetic field changes at a uniform rate from 2 Tesla to 9 Tesla in 14 seconds. Now, the coil has an area of 2 square meters. What is the EMF? Okay, so this area and then my B initial equals 2 Tesla. My B final equals 9 Tesla. And my delta T equals 14 seconds. Just so you work through it. Can you do that for me, please? Okay, so let's do this. So we're going to turn around and say, well, first of all, let's write down Faraday's law, which is that my EMF is equal to minus N d phi B by dt. And then I'm going to turn around and say, well, hold on, I also know that my phi B is equal to integral of b dot dA, which equals the magnitude of b times the magnitude of a times the cosine of the angle between. So then I say, well, okay, my flux is equal to minus n d by dt of BA cosine the angle. So the next thing I need to do is need to take out all the constant things. My integral kind of went away somehow. So, oh no, it went away there, yeah. Then I need to take out all my constant things to the front. So I'm going to say my n can come out, and my b can, my a can come out, and the cosine theta can come out, and that leaves me with dB by dt. And in the nice uniform form, I can say that's delta B by delta T. And so my flux is equal to minus NA cosine theta. And I can even add that down as B final minus B initial over delta T. So then my flux is equal to minus N, minus 40. I'm looking at my diagram now, times my A. And my A is equal to, what did I say, 2 meters. My cosine theta, and in truth, I didn't give you any information about that, and I should have done. And if this were a test question, by all means, put your hand up and say, well, what direction is this in? I suppose as a little fig leaf, you know, to cover my embarrassment, I could turn around and say, well, with no other information, assume it's at 90 degrees. But you could say, well, with no other information, assume it's going through perpendicularly. And I could say, well, with no information, assume it's going through like that, in which case the answer is 0. So, you know, hey, I really got to tell you what it is. But in my mind, I meant to say that the B is perpendicular to the plane, is that the right way of spelling, of the coil. Yeah, that's what I meant. So then this is that times that times that, and then this is cosine theta. So this would be cosine of 0, because my A vector is perpendicular. So my A vector is perpendicular to my B vector. So that's cosine 0. Parallel, I meant parallel, yeah. It's perpendicular to the plane of it. It's parallel to each other. That's what I meant. And then I have BF would be 2, actually, isn't it? Oh, no, 9. Well done. 9 minus 2 over, and my time integral is 14 seconds. So E is going to equal minus, let's have a look, 80 times 7 over 14, which equals basically minus 40 volts. I kind of made heavy work out of that, but so quite doable. Yep. In this one, I'm going to turn the area in time. So I have a coil which is n equals 10. Strength of the magnetic field that passes through the coil is 12 Tesla. I'm going to tell you now it's perpendicular to the plane. The coil is an area which changes. So A initial equals 3 meters squared, and A final equals 7 meters squared, and my time interval delta T is equal to 5 seconds. And it wants to know, what's the EMF? How can I change this area? There's ways I can do it. Not so easily for a coil, but for a loop I could do it very easily. So, okay, I'm going to say, well, Faraday's law. Faraday's law says that my EMF equals minus N d phi by dt, which equals, and also my phi is equal to B dot dA, which equals B times A times the cosine of the angle between. And I bring you guys together and I go E is equal to minus N. It's going to be d by dt of B times A times the cosine of the angle between. So then I say, well, hold on, in this case my B is constant, so let's bring that out. And my cosine theta is constant, so let's bring that out. So I have d by dt of A, which equals minus NB cosine theta delta A by delta t, because it's nice and steadily changing, which is minus NB cosine theta, which is A final minus A initial over delta t. And now I'm looking at my diagram and I'm going to go E is equal to minus N, N is 10, B, my B was 12. My cosine again, I'm going to assume parallelism. So that's going to be 1. And then I'm going to go, my final is 7 minus my initial is 3 over my time is 5. So that's going to equal 120 times 4 over 5, which would equal 12 times 8, which equals 96, I think. Is that right? Yeah. 96 volts. And it's minus, of course. I'm just dropping my negative sign there haphazardly when I shouldn't. So that's that. Cool. Okay. I'm going to try and do the last one because it just completes this little thought. And there's a common mistake with this last one. So I have a coil which is 15 turns. And I have a magnetic field is 12 Tesla. And the area that's going to be 3 square meters. But what I'm going to do is I'm going to spin it. So if I have a little diagram here, I start off, the angle between the magnetic field vector and the area vector changes from 25. So I start off with, I start off with that being 25, and then I spin it so that I get, so that's 25 to begin with between my B and my A, and then I end up with that being 70. Yeah, so turning the thing. Yeah. So I say, oh, you're joking. Go away. Okay, sorry about that. So then we say, well, Faraday's law, E is equal to minus N d phi by dt. And I say phi is equal to BA cosine theta. I'm going to rush this a little bit. So I say E is equal to minus N d by dt of BA cosine theta. And then I say, well, okay, take everything out that's common. That's so N, B, A, N, B, A. I have d by dt of cosine theta, which equals minus N, B, A delta cosine theta over delta t. So E is equal to minus NBA. and it would be cosine theta final minus cosine theta initial over delta t. So E is equal to, now I'm looking at my diagram and I'm going to go 15, I'm going to go 12, I'm going to go 3, and then I say multiplied by, and I get my calculator, which is in my jacket pocket in my office. Can you believe it? So what is cosine of 70 degrees? Pardon? What? 0.663. Oh, sorry, yeah, thank you. 0.663. And what's the cosine of 25 degrees? 0.991 divided by my old friend the time, which is 4 seconds. Thank you. So can you work that out for me, please, and get me an answer? It's going to be 180 times 180 divided by 4 times whatever that difference is. Shame on me, I should have a number for this, but
I'm sorry, but I got cosine 70, I got.
Yeah, I did mine in radians.
34.
0.34, can we check that again?
No, I did mine in radians, that's why it's wrong.
Oh,
Degrees, it's
yeah, I got to be in degrees then, so that's 0.34. And what's the first one?
0.34.
No, what's the final, what's the cosine of 70 degrees?
Yeah, 0.34.
Oh, 0.34. And what's the cosine of 25 degrees? What's correct?
0.91.
Oh, I see. Okay, thank you. So then work that out for me. So a number, yeah? So what is it? What specifically is the number? It's going to be, that's about 0.6. 307? That's, no, yeah. All right,
76.95.
76.
0.95.
What do you think the big error is on this? When I'm grading this, pardon? Exactly. People will go, oh, that's easy. I'm just going to take away the angles and do the cosine of the difference, which is not the same as taking away the cosines. That's the most common mistake in that. People do all that hard work. It's going to be volts. Yeah, sorry. They do all that hard work and then they find that and that's it's again going back to just, that's why we keep using math, is to keep practicing it. Okay, I'm going to stop there.